Assalamu alaikum warahmatullahi wabarakatuh. Dear brothers and sisters, good evening. Today, our lecture number 5 or session number 5 in Introduction to Oil and Gas Industry. Today, we will continue speaking about the reservoir and wellhead. So let's speak about the agenda for today's session. Speak about the wellhead. We'll go through the subsea wells, the injections, and the artificial lifts. We'll go through all type of artificial lifts, the root pumps, the ESP, the gas lift, and the plunger lift. So first, let's speak about the wellhead. In the previous session, we spoke about the drilling itself and the well and how the well consists of casing and a lot of things, which is subsurface. Today we will speak about the surface itself, the above surface, the wellhead. So the wellhead. What is the wellhead? Actually, the wellhead, it can be installed onshore or offshore. The wellhead actually is a group of valves. It's like an equipment, as you can see in the photo here. This is the wellhead. It consists of a group of valve. As I told before, the meaning of valve is for controlling the flow, for closing the flow, for regulating the flow. It is mainly for the flow coming from the well, to control the flow. So this wellhead that you can see on the platform is actually on the well. So if you go down here, you imagine the well will be down. So this is a wellhead on the top of the platform, on the surface. And as I said, it has a group of valves and blowout prevention. This blowout preventer, it prevents the flow that's coming from the well from any disaster to blow out immediately because of the high pressure that's typically on the wellhead. So it's also protect the flow from any gases or liquid that can escape from the well. So the well here, down, down, down. So it starting from drilling, the gases and liquid will escape and will scatter, will blow out. So this wellhead structure or equipment will prevent and protect the gases and oil from blowing out or from escaping around. So this is also for safety and controlling purpose. And as I told also, to regulate the pressure. The pressure that we have on the well, it's very high pressure. We all know that the well is always, all the time, under very high pressure because of the layers of the ground and the layers of the land, many layers. And the source of oil or gas may be found at very deep distance, maybe it can reach about 4,000 tips, 4,000 meters. So you can imagine the high pressure occurs on this situation or in this condition. So if you start to drill under this high pressure circumstances, the flow will immediately blow out. So you have to control it using this group of valves. You have to control it using the blowout preventer. And the other group of the wellhead is called the Christmas tree. The Christmas tree, as I told, is one of the components of the wellhead. So the wellhead is basically contains of casing head, the tubing head, and the Christmas tree. The Christmas tree is actually composed of master of valve like a pressure gauge, wing valve, swab valve, choke valve, as shown in this photo. There is another photo also of the wellhead. Here, this section shows a group of wellhead, shows a group of valves on the wellhead, and the above section, this section, it is a Christmas tree. It is well known in the oil and gas industry. So you have to remember this terminology, Christmas tree, Christmas tree. So be alerted if I may ask this question. So what is a Christmas tree valves? It's actually a group of valves, swing valve, choke valve, pressure relief valve. Pressure valve is to control the well, to control the well. Another photo of the wellhead and Christmas tree. This contains a group of valve. For example, this wing valve is enabled to kill the fluid which is pumped down to the well. This valve is called swab valve or pressure gauge valve. It's actually allow access for well and workovers. This also here side valve is called flowing valve. It allows the well to flow. So it's actually give the permission to the well to flow. Here is the master valve. This master valve is mainly the valve that isolates the well. So this is a master valve. So if it is closed, so the well is closed. If it is open, then the flow from the well will flow, will pass. And this is the wellhead, and this is a production tube that's going through the well deeper. This is group of annulus valves to monitor the pressure in the annulus. And annulus actually is a pipe, small pipe that places the tube inside it. So as I told, the wellhead assembly, is the photo here, is used actually as a connection for blowout prevention, POP, during drilling, and the Christmas tree during production. So the POP is mainly during the drilling to control the flow from blowing out immediately while I am doing the drilling. And the Christmas tree is to control the flow and the well during the next phase, which is production. And the other function of the wellhead is to hang down whole tubing and casing string, is mainly for supporting and hanging the tubing and casing string. Also, it can act as a sealing tube casing and tube casing annulus. Sealing is the opposite of leakage. We know, right? We know the leakage or sweeping. Leakage is something that's leak and you want to control it from going somewhere. So you have to seal it. So actually the wellhead, this wellhead is work as a great sealing of the well. It is to be sealed from any escaping, the flow will escape somewhere. The other function of this wellhead is allow access into the production and annulus. So it is actually can be a part of production, this wellhead. And also it can also part of production by injection of steam or gas or water or chemical. And we will come to this part of the injection and why we need to do some injection to the well in the next slide. So as I told, this is a group of blowout preventer. This mainly during the drilling to control and to monitor and to protect actually the well from blowing out during drilling mainly. This is group of valves for controlling purpose. Again, blowout preventer is to control the flow from blowing out during drilling because of high pressure. Because of what? High pressure. Again, this is a wellhead, which is typically consists of casing head, casing hangers, tubing head, tubing hangers, and tubing adapters, and a group of valves, as you can see. Another photo of the wellhead, another assembly. There is actually some manufacturing company you may know some of them, and they actually well known like Schlumberger, Baker Hughes, Technip, Baker, Wood Group. Actually, those are mainly vendors and suppliers and manufacturers of the wellhead equipment and the Christmas tree that are well known globally in the market and in the universe worldwide. So this is the basic arrangement of the wellhead and Christmas tree. As I told, the master gate valve is mainly to isolate the well. It's actually very high quality valve. This master valve is very high quality, and it's open and close the well with the same diameter of the tube itself. So this master valve, it should be capable enough to handle the required pressure and required capacity of the flow, because it is really mainly for isolation, and it should be left open, without closing. The swap valve and the gauge valve, pressure gauge valve mainly is an instrument device, is to measure the pressure, and this is really important because we want to know the pressure inside the well. We need to monitor it, and it has to give this transmittal to the blowout preventer to control the pressure, or the pressure control valve to either open or close as required as per the pressure on the well. It is mainly for pressure gauge first, and then pressure transmittal to transmit the pressure to the pressure control valve. The ring valve and the other valve, like ball valve, is like it's working when we shutting in the well, and it's actually used in tubing pressure, and it can be also easily read. And the choke valve, which is located here, this is choke valve. It's merely for the flow. It is to control the variable flow. We have variable flow, and it has very large needle valve. So it is required to control the variable flow. So let's see this small video about the wellhead, and we'll back again. Sorry, I will share again.
Welcome to the ADCO Learning from Incidents series, Well Control and Blowout Prevention. We will be sharing with you some information on well control during drilling, the various systems put in place to control a well and prevent a blowout incident from occurring. We will also review the main reasons behind some of ADCO's well control incidents which were handled successfully. Prior to the preparation of the drilling program, the asset development team submits the final well prognosis to the drilling team. The well prognosis is initiated by the petroleum engineer. The reservoir engineer then makes a planning overview and provides the required formation pressures and temperatures. Then the following data is completed: geodetic data, conceptual data, geological data, reservoir data, geophysical data, and petrophysical data. Once all the data is entered, the well prognosis will be approved by the Reservoir Operations Asset Team Leader and will be published in ADCO system. Let's begin by explaining well control. While drilling, it is essential to perform activities in a safe way, which will prevent uncontrolled flow of formation fluids and gases from the reservoir to the wellbore and surface surroundings. This is called well control. This includes measures, practices, procedures, and equipment, workover and completion, as well as the installation, repair, maintenance, and operation of surface well control equipment. It also consists of well control barriers, which are divided into two groups: primary and secondary barriers. The primary well control barrier is the fluid column hydrostatic pressure, referred to as well bore pressure, that provides overbalance against the formation pressure. This column must be monitored and maintained during drilling and tripping to prevent formation fluids from entering into the wellbore. During drilling, if the fluid column is not maintained with adequate mud density, making the formation pressure more than the hydrostatic pressure, formation fluids will find a way into the wellbore and a kick will occur. In this case, the well must be secured and killed. There are other cases when a kick can occur. Let's review some of them. While tripping, if there is a failure to keep the hole full of mud to maintain adequate hydrostatic head, then the hydrostatic pressure will be less than the formation pressure, inducing a kick. Swabbing while pulling out of a hole too fast can produce a suction effect, resulting in a decrease in the bottom hole pressure large enough to allow formation fluids to enter the wellbore, creating a kick. When drilling takes place too fast and into depleted reservoirs without proper reinforcement, it can lead to cracking in the walls and thus losing fluids into the formation, inducing a kick. Once a kick is detected, the secondary well control barrier, blowout preventer, BOP, must be activated immediately by the driller to secure and shut the well for killing operations. This is done by closing the BOP using one of the BOP control panels, one situated on the rig floor and the second situated in the Kumi unit. The driller will shut in the blowout preventer to stop the flow of formation fluids out of the wellbore. Then, he will activate the alarm and notify ADCO drilling supervisor and rig manager. Meanwhile, at the rig site, the on-scene commander, ADCO drilling supervisor, will notify Abu Dhabi telecom operator and relevant assets control room and raise emergency Tier 1, which activates appropriate emergency response teams. Unnecessary crew will be evacuated to the nearest assembly point. The next step will be to monitor the shut-in drill pipe and the shut-in casing pressure gauges. The kick will be circulated out of the wellbore using the driller method first cycle by pumping drilling fluid downstream and getting returns from the annulus through the choke line to the choke manifold, and the pour-buoy degasser and toxic gases will be flared. Once the kick is out, the well will be shut in. Then, the well will be killed with weighted mud by circulating the kill fluid until both the drill pipe and casing pressures reach zero. If all of the well control barriers failed, such as human barriers, BOP equipment barriers and system barriers, and the BOP leaked while circulating the kick-out, this could lead to uncontrolled flow of formation fluids and possibly a blowout. A blowout has massive catastrophic consequences, such as injuries and/or fatalities of personnel, release of toxic gases, pollution of the environment, asset damage.
So notice here, please be alerted. It can cause fire. Explosion will happen if we don't have the proper control. This is very important in the oil and gas industry. To control the oil and gas, it is more important than operating it. We have to control it. This is mainly one of the basic things in the oil and gas industry. Start from upstream throughout the system, down midstream and downstream and refinery. Without controlling, a lot of incidents may happen. As you can see here, the blowout happen because the blowout preventer is leaking. It's not working well. And then explosion happen. And as you can see, it can lead to a lot of injury and accidents and fatalities of personnel, as long as a disaster in the economy and a lot of environmental impact and pollution and the assets will damage. It is many issues. So controlling the oil and gas, these flammable gases and these volatile gases, this is really easy to ignite and easy to make fire, is more and more important. Okay.
And damage of ADCO's image and reputation. ADCO strives to create a safe and
Okay, so this is, I just want to share this with you about the importance of controlling the well and how we control it using the blowout preventer as the last stage of controlling. Let's speak about the types of well. What is the types of well? We have different types of well. We have either wellhead types that can used for production, or we have wellhead that is mainly for really artificial lifts. So the artificial lift, that is mainly the wellhead that is easy, that you can lift the flow out from the well. However, the production phase, the wellhead that's mainly for production, you can put some injection And this injection, you can inject gas or water or whatever. This is mainly for facilitate the oil to be produced. So there is some plant, it's called water injection plant, is mainly to inject water in the well to reach some certain pressure that allows the oil to move or to allow to reach to some certain pressure that can allow the flow of oil and gas to reach to the surface. They need to inject water and inject gas. So there is some certain plants is mainly for this purpose. This is the injection. So as I told, sometimes the wells, as I told, is divided either for production well or injection well. And the former are for production of oil and gas. So this mainly that we need well for production. However, there is some wells, it's mainly for injection, not for production. And this is only, as I told, is to inject gas or water into the well. So you are doing the process in an opposite way. Instead of sucking the flow from the well, you are injecting a flow. And this flow that you are injecting in the well is gas or water. What is the purpose of that? The purpose of injection is to maintain overall hydrostatic reservoir pressure. You want to maintain the overall hydrostatic reservoir. You have a great reservoir. You want to maintain the overall reservoir hydrostatic pressure. So you want to inject the pressurized water or gases to maintain this hydrostatic pressure of the reservoir. This is one reason. The second reason is to force the oil towards the production. So the second reason, you need to force the oil that is already exist in the reservoir. You need to force this oil which is static. You cannot actually draft it or suck it. You need to force this oil to the production well, which you called injection water breakthrough. So this is injection wells, as I told, it's very important. It is fundamentally the same as production well heads in the basics, but it's a difference between them that the direction of the flow. The injection, we are injecting downwards. However, the other production well, we are sucking upwards. This is very important. We need to focus on this one. What is the artificial lift? Okay. The production well, sometimes they are free to flow the fluid. So the fluid or the flow, it can be easily lifted. Freely without any force or power or pressure to reach a suitable wellhead production pressure and to maintain acceptable well flow. So you need to have well flow requirement and you need to maintain a pressure which will be sufficient to reach to the surface. So sometimes it is free of the flow to reach itself without any pressure. However, if the formation pressure it is very low, you need to do something from your side to lift the flow from this low pressure to the surface, up to the surface. You can you can do this by a type of artificial lifts, like this method. You can do gas lifting, you can do beam pump or rock pump, you can use hydraulic pump, you can use electrical submerged pump. You can use plunger lift type. So there is many types that you can use to force the flow or the oil to be lifted to the surface. Because of what? Because the flow itself, the formation pressure is very low, and the injecting water or gases is not enough to force this flow or formation flow to reach to the surface. So we have to use another alternatives or another external forces which called artificial lift to suck this flow up to the surface or to force it by the machine to the surface. So let's see this video and we'll come back again to describe more about the lifting. So we have different type of artificial lift. You can see here in the small video, it will explain. The first one is the rock pump. This is pump. As you can see here in the photo, in the video, it is suck or pumping the oil from the well and lifting it up to the surface using this pump machine. It's called beam pump or rock pump. This is rock pump using pumping. Pump or rock pump. This beam pump is to suck or shift or lift actually. This is exactly the main terminology, to lift the oil up to the surface. So the other type is using progressive cavity pump. There is BCP, progressive cavity pumps. These pumps will be on the surface, as you can see here on the video. Then it will be drilling, going down to the well to lift the oil up to the surface. When we are using this again, if the formation pressure is very low and cannot be reached freely, and also the injection water or gases cannot also force the oil. The other type is gas lift system. Gas lift, we are injecting gas with high pressure, and this gas actually will go deeper and then will force the oil, as you can see here, to up through the annulus tube or through the well. So the gas you can see here in the yellow, this is gases, will go down, injecting gases, and these gases will force the flow. You can see here the flow. This is the bubbles of the flow. So the flow can be now lifted up through the annulus. The next type is plunger lift. Plunger, this is plunger. This is the red color. This is plunger tube. And this is actually a machine to push this plunger to suck or to lift the flow. The flow is here lifted. So the plunger again will go down through the well, deeply through the well, and then is pushing with pressure to lift the flow up. So the flow now is lifted up using this plunger artificial lift type method. Another type is hydraulic lift system. Hydraulic is mainly hydraulically using oil mainly. So also is close type to the plunger, but it is hydraulically, not mechanically. So this is many different types of artificial lifts. As I told, this is mainly to force or lift the oil or the flow, which has low pressure, and the pressure cannot actually allow the flow to reach freely without any force. So the force.
Gas lift is an artificial lift system where gas is injected into a produced well's cage.
So the formation pressure is very low, so it cannot reach automatically. So we have to use mechanism like this. So this is the first mechanism, the rod pumps or the beam pumps. As you can see here in the photo, this is why it's called beam, because this is the beam here, and this pumps because it has motor and gearbox, and this is stuffing box and the discharge. The discharge will come from here, and it will go deeply like this to lift the oil. So It is called also sucker or road bumps or donkey or bead bumps, as you can see here in the photo. Another photo also of the root bumps and bead bumps. This is also the same photo of the root bump and the bead bumps. It is an easy mechanism to lift the oil from the well. Another also mechanism or photo of the beam pump. This is a beam pump you can see here, and it's actually going down to the production oil to suck or lift the oil up to the surface. Let's have some video about this one so that it will be more easy to understand the type of beam pump.
احجز فندقك أو تذكرتك بأفضل الأسعار وسدد على دفعات. حمل تطبيق المطار.
لبنة بريزيدون التركية الأصلي. 100% حليب بقري طازج لا تقاوم.
How's it going, guys? My name is Derek Craig here with Oil Food Basics. We're here at Merida College's Oil and Gas Technical Exhibition 2018. It's our second annual one. And I'm here with Scott Gillespie here with Harbors and Fisher. And he's going to walk us through this amazing model here that we have on display that's just showing the basic operations of how a rod lift or pump jack system works and how it lifts the fluid to surface. So Scott, you want to walk us through it?
Okay. For instance, this would actually be a clear version of what a pump would actually look like.
And this is all the way down in your formation,
yeah,
right?
this would actually be seated,
not near this close
seated in the tubing in a seating nipple down inside the tubing.
Okay.
You would actually have, this is your plunger here, this would be your pump barrel. You'd actually have a cage here with a valve in it. This would be your traveling valve. And then you actually have another valve here seated in the seating nipple, which would be your standing valve. Mm-hmm. And on the startup of the actual unit, the traveling valve ball opens, comes off a seat, opens and lets you go downwards. You're actually grabbing a scoop of fluid and lifting it to the surface. Mm-hmm. So the balls and seats actually work in conjunction with each other. When one of them's open, the other one's closed, then the other one opens and the other one closes, and you're basically just repeating the cycle and actually bringing that fluid back up into the pump chamber and actually lifting that column of fluid to the surface.
Okay, and the fluid travels through your tubing?
Through your tubing,
the surface, right?
Up to the tank batteries on surface.
Gotcha.
This is actually a single valve version. There's only one valve on the traveling valve, one on the standing valve. We can actually double valve those.
Okay, and the benefit to double valving is?
Just kind of a backup, kind of a security type thing. This valve, because if one of these valves, if a piece of sand or particulate gets trapped up under it and it actually can't seat, it won't work. So,
gotcha.
There's a chance you could actually have to pull tubing and to get, or actually pull the pump to actually retrieve it and fix the problem. So,
very cool. And is there any type of particular problems that you can show us that are common with pump jack wells with this model?
What we like to see is actually pumping long, slow strokes.
Okay.
A lot of people have a tendency to go in and over pump their wells. We want to actually just pump the amount of fluid that the formation's actually given up. Okay. If you overpump your wells, you can create some problems and issues, especially, that's when it gives time for the particulates to settle in down on your pumps, and sand is a big issue on shutdown periods and things like that. So we try to pump them long and slow strokes.
And it also helps with better efficiency.
It helps
right?
better efficiency also. As you can see, the fluid, everything's moving kind of nice and slow, and everything's. If you start to speed it up and over pump it, you'll see what happens. You're actually introducing a bunch of agitation and a bunch of things into the actual where you're not getting, and then eventually you'll get to where you're not getting full fillage on your chamber here. And then when it does come down, you're actually going to smack that fluid and create what they call fluid pound.
Okay.
So the longer the slower strokes, the better efficiency you'll actually get. And then as I speed it up again, you can kind of see what happens.
And can you talk a little bit about the wear that this causes on a system?
What's that?
The wear that this causes on a system if you're pumping too fast?
Yeah, if you're pumping too fast, especially if you get this void in here, that shock wave when that actual valve hits that fluid, you know, it's actually, you can actually tell when a pump is doing that because you can actually feel it clear into the bridle. You actually.
Okay, I think this is good enough to know about the pin pumps and how it works and how it operates. This is like a sample from the office from the drilling company. They are using in their office to show to the trainees or to the people that they are newcomer to the company how it works, how these pin pumps works, how these pin pumps works physically. So the other type is from artificial lift is the ESP. ESP is actually stand for electrical submerged pump. Electrical submerged pump. As you can see here in the photo, this is a pump. This is submerged. So how it is submerged? It's submerged through the well deeply using wiring and cabling, and the pump actually is going down and they have some suction and intake and the motor, everything in the world. But the purpose of that is to lift the oil to the surface. The oil should be lifted to the surface through this ESP. Okay. So this is another photo of ESP also. It is, as you can see here in the photos, from produced fluid. It goes through this motor, and this is a motor, and then go to this pump intake. So it is submerged, as you can see, this pump intake. And then this is a separated gas here. And this is a power cables, and it will go to the surface, up to the surface. So it's controlling here with this blowout preventer. And this is piping that is connecting for the discharge of the flow. So this is electrical submersible pump or ESP. It's very common use in the industry. Another type is called gas lifting. Gas lifting is basically that you inject gas down to the well, and then this gas will force the flow to go up. This gas will force the flow to go up. Let's open this video to see. So it's not working, no issue. Anyway, so this gas lifting is mainly to lift the oil, but injecting gas, and this is can reach to the 150 megapascal reservoir pressure, and the depth can reach up to 1,600 meter depth. The other type is plunger lift. As we also saw in the last video, the plunger is, instead of gases, you are inserting plunger, and this plunger actually will push the fluid to be lifted up through the well. And this is actually normally used this type for the low pressure, gas wells. Okay, the last thing that we will speak today about is the subsea well. What if that we have well on the subsea? As you can see here in the photo, the subsea wells actually are essentially for the dry completion wells. It's actually, instead of putting the wellhead and all this equipment on the surface, on the platform, we'll put on the seabed. Because it is on subsea. We are working now on the subsea. And this is mainly in the offshore industry, not onshore industry. It is mainly for the offshore industry. So let's see this video about the subsea well. It will be very useful about it.
Shell Deepwater is fueling the growth of upstream Americas by safely developing new reserves and maximizing the potential of its existing producing assets in the Gulf of Mexico, Brazil, and Venezuela. Drilling a safe, deep-water well can take years of planning and preparation. After identifying potential oil and natural gas reservoirs beneath the seafloor using seismic technology, a drill site is selected. Shell geoscientists choose the drill site location on the seafloor based upon the safest well path that will encounter the targeted oil and natural gas. For an exploratory well, in water depths up to 9,000 feet deep, this seafloor location is generally directly above the reservoir. A drilling rig is required to drill a well. In deep water, the rig may be on one of three vessels: a drill ship, a semi-submersible vessel, or it may be part of a floating production platform. All rigs have a hoisting system to raise and lower the drill pipe and tools needed to drill the well, a blowout preventer or BOP stack, and a pumping system to circulate fluids in and out of the well while drilling. It's time to drill the hole or well bore using a drill bit. This initial step is called spudding in the well. The shallow sediments just below the seafloor are often very soft and loose. To keep the well from caving in and carry the weight of the wellhead, a large diameter base pipe or casing is drilled or jetted into place. The base pipe is assembled at the rig floor, and a drill bit connected to a drill pipe is run through the inside to the bottom of the casing. The entire assembly is lowered to the seafloor by the rig hoist. At the seafloor, the driller spuds the assembly into the seafloor sediments, then turns on the pump. Water or a drill fluid is used to jet the pipe into place until the wellhead is just above the seafloor. With the base pipe and wellhead at the right depth, the driller will release the bit and drill string from the jet pipe and drill ahead. While the well bore is being drilled, mud is pumped from the surface down through the inside of the drill pipe. The mud passes through the jets in the drill bit and travels back to the seafloor through the space between the drill bit and the walls of the hole. Drilling mud is used to 1. Lift rock cuttings from the hole, 2. Keep the drill bit cool and lubricated, and 3. Fill the well bore with fluid to equalize pressure and prevent water or other fluids in underground formations from flowing into the well bore during drilling. The mud is an environmentally friendly water-based mixture of clay for thickness and fine ground rock or barite for weight. At the planned depth, the driller will stop drilling and pull the bit out of the hole. A smaller pipe or casing string is then screwed together, connected to the drill pipe, and run down to the seafloor and into the well. To permanently secure the casing in place, cement, followed by mud, is then pumped down the inside of the drill pipe. To separate the cement from the mud, a cementing plug is used. The plug is pushed by the mud to ensure the cement is placed outside of the casing, filling the annular space between the casing and the open hole wall. On some locations, a second surface casing is needed, thus the well is drilled even deeper. In this second surface casing interval, the well is cemented using a second smaller casing string, repeating the same process used in the last hole section. At this point in the well, the pressure in the deeper rock may be too high to continue with the simple water-based clay mud, or there may be the potential to encounter oil or gas. Before drilling below this point, a blowout preventer with a riser will be installed at the seafloor. The BOP stack is a massive system of valves and rams that protect the rig and environment from oil and gas flows should the weight of the drilling mud be too low. The BOP stack is connected to a pipe called a riser. The riser connects the rig to the well and allows us to circulate the drilling fluid and rock cuttings all the way back to the rig on the surface. The BOP stack is fully tested before we drill further. Drilling now resumes with the drill bit and drill pipe always operating through the BOP stack. Just as we did further up the hole, casing strings are run and cemented in place when needed to cover up the open hole sections. When the oil and gas zones targeted by the geologists are reached and the presence of an oil or gas zone is proven, a final casing string may be installed if the seafloor location is favorable for future development. This final casing string allows for the future safe production of the oil and natural gas.
So that's all, dear brothers and sisters. We finished today's lecture. I will now ask some questions to know if you really got some basics about today's session and to refresh our memory as well. So the first question that I will ask now, let me stop the recording.